All right, so let's continue with our notes here. We're on page 9. Sure. Right, so we got a chance to go through unit circle. We didn't get a chance to do much of this, right? So yeah, let's see if we can fill out 30. Did we do this 31 to 45? No. We haven't. Okay, all right. So yeah, use your unit circle and see if you're able to find these mostly first quadrant values.
Should we get to the point where like we'll have to like know where each stuff is without looking at like drawing unit circle or hills?
I would say it's okay to draw, but I would say only draw out the first quadrant, right? You should be able to get everything you need from the first quadrant. Yeah, so we shouldn't have to spend 5 minutes doing this whole thing just for one problem, right? I think this is fine though. This only takes a few seconds, right? So
we'll definitely need to notice for like calculus topics, right?
I'm sorry?
We'll definitely need to notice for a calculus.
Yeah, just as background, right? So when we get to the point where we're finding derivative and then we're solving, a lot of times at the very end, we have to be able to evaluate a trig value, and we need to be able to get to the answer quickly without having to, spend 5 minutes doing this last portion of a calculus problem. As far as secant and cosecant goes, sometimes I like to just think about the easier one first. So I know secant and cosine are related. So if I know what cosine of pi over 2 is, we know cosine of pi over 2 is 0. So secant is going to be flipping that 0. So if I flip that 0 to the denominator, then it's going to be undefined. So that's how I know secant of pi over 2 is undefined. Same thing here, cosecant of pi over 2. I like to think in terms of sine to begin with. I know sine of pi over 2 is 1. So if I flip 1, I still get 1. Okay, any questions so far? Yeah.
So you can put 0 and 2 pi in, like you can just put like 0 or 2 pi. Probably should put both.
For which one?
44.
Yeah, 44. The reason why we include 0 and 2 pi is because our domain includes 0 and 2 pi. So if 0 and 2 pi is a solution, it needs to be included because of the domain restriction that we see there. But technically, there's infinite solutions because we can keep adding pi and get more solutions because tangent will keep crossing 0. But we have these intervals to restrict the solutions. 43, for instance, here, sine is equal to 1/2. We know sine is 1/2. First quadrant is pi over 6 in that pi over 6 family. So I know it's pi over 6, and I know that sine is also positive in the second quadrant. See that S there. And also my order pair, I know that my y value is positive in the second quadrant. So I know that I'm also getting a positive 1/2 as well. So the second quadrant variation of pi over 6 is 5 pi over 6. So I have those solutions there. And they both fall nicely within my interval from 0 to 2 pi. Okay, any questions with this page? Okay, just want to graphing trig functions is not that important, but I think it's just good to recognize what the graphs look like. So a sine and cosine graph are very similar to each other. Sine starts at 0, and if you just look at the the y values of your unit circle, you can plot those points pretty quickly. Cosine is the x value, so it starts at 1, then goes to 0, then goes to -1, and then goes to 0 and back up to 1 again. So if you know that, your unit circle can kind of help you create the shape of your sine and cosine. Tangent and cotangent look similar in the sense that they look like they are negative and positive slopes of each other. Tangent is positive slopes. Cotangent is negative slopes. Tangent has period of pi, so it's going to keep repeating its period every time we reach that interval of pi. Cotangent is the same thing. It's just more of a negative slope look to it. And then cosecant and secant are just basically these kind of parabolas looking shapes that look to build off of the sine and cosine. So if you know what the sine looks like, then wherever there's a 0, you can drop an asymptote, and wherever there's a peak and valley, you can draw these parabola looking shapes that will be your cosecant graph. Secant, same idea here, where whatever my cosine graph looks like kind of acts as a background to help me shape my secant graph. Wherever my cosine hits 0, I can drop a vertical asymptote, and wherever there's a peak and valley of my cosine, we see these parabolas. Okay. Okay, so I'm not going to do all of these. Some of these I'm going to ask for you guys to do for homework for me to check on Monday. But I just want to pick out a few of these. Let me pick out these here. So 57, 60.
You were 62.
Yeah, I'll do 62 and 63. Okay, so it says solve the following trig equations where x is between 0 and 2 pi.
That goes bad.
I know, I'm driving sad. So we only want to produce solutions between 0 and 2 pi. And so first, cosine is equal to √3/2. Well, we know that cosine is going to be in that, when cosine being √3/2, that's going to be in that pi over 6 family. So we can say pi over 6. But we also know that cosine is going to be positive in the fourth quadrant. So the fourth quadrant variation of pi over 6 is going to be 11 pi over 6. Okay, number 60, cosine of x over 2 equals root 3 over 2. Now, this one feels a little more complicated because it's not asking for cosine of x, it's asking for cosine of x over 2. So what I like to do here is I like to use inverse cosine to just help me isolate that x over 2 by itself. So I'm going to say x over 2 is equal to inverse cosine of root 3 over 2. Now, this means the same thing. I'm still looking for the radian measure where cosine of theta is equal to root 3 over 2. So I'm going to get the same solution as above, right? We know that cosine of theta is equal to root 3 over 2 when theta is equal to pi over 6. And when theta is, or when x is equal to 11 pi over 6. So I know that this portion is the same as these here. So now that I know what this is equal to, I can replace this with pi over 6, and then I can just get it into an algebraic equation for me to solve for x. So I know that for one of them, x over 2 is equal to pi over 6. If I cross multiply, I can solve for x. 6x equals 2 pi. Divide both sides by x. 2 pi over 6 is pi over 3. So that's one solution. The other solution is 11 pi over 6. I can replace 11 pi over 6 into this inverse cosine of root 3 over 2. Cross multiply, I get 6x equals 22 pi. Divide both sides by 6. 22 over 6. The same thing as 11 over 3. But the problem with 11 pi over 3 is that this is more than 2 pi, right? So if it was 6 pi over 3, that would still be within the interval, but 11 pi over 3 is already further out than our domain, so we can remove it. It's not part of our solution.
So cosine, like inverse cosine of root 3 over 2 is the same thing as saying like cosine equals 3.
Yeah, so inverse cosine of root 3 over 2. So if I had cosine of x is equal to root 3 over 2. Okay. We know that x will be equal to pi over 6. Another way to write this is to get that x by itself and move that cosine over. So x is equal to inverse cosine of root 3 over 2. It's the same thing. It just allows us to rearrange that cosine in a different place, but these tell us the same thing, which is able to isolate the x in this instance. But x in both cases would be pi over 6. (11 pi over 3 is a variation of 5 pi over 3, but it's further out than 2 pi. All right, so it's going past my domain. So it is a variation. It is a solution, but it's just not. It's a coterminal angle, but it's too far out. All right, 62. Again, that 2x is causing us some additional work here. We know we are going to find where sine is equal to 1, but let's just go ahead and isolate that 2x by itself so that we can just focus our attention and work on two different things at once. So this side is basically saying, where is sine equal to 1? Right, so where is sine equal to 1? What theta value? Yeah, pi over 2, right?
5 pi over 2.
Right, so what we're going to do is we're going to go further out than 2 pi. And the reason why is because we're expecting to divide by 2 to solve for x. And when we shrink these values down, we want to make sure that we have all of these covered. So we're going to go a little further than we normally would. And we can always find coterminal angles by adding 2 pi. And adding 2 pi, in this case, to match with common denominator will be the same thing as adding 4 pi over 2. So I'm going to say 5 pi over 2 as a potential solution. If I'm going to go one step further, just so I can just, I want to make sure I have more than enough. so that I don't accidentally miss something. So if I keep going, I could also have 9 pi over 2. Now, these are the potential solutions because we still want to divide by 2 or multiply by 1/2 because these values are going to shrink, and we want to make sure that when they shrink, that we are not accidentally missing out on some solutions that's going to be closer to 2 pi. So if I divide everything by 2, or in other words, multiply by 1/2, I'll get pi over 4, I'll get 5 pi over 4, and I'll get 9 pi over 4. So it's good to see one that is further out than 2 pi. So I know that I've covered all my grounds. I can remove this one. So I have 2 solutions that fall inside my interval.
Do they call it an extraneous solution when it's too much?
Yeah, extraneous solution because it's outside my interval, right? Okay, you guys want to try 63? Approach 63 the same way that you would approach 60. Find the inverse sine of root 3 over 2. Or find where is sine equal to root 3 over 2, and then set that equal to x over 4, and then solve for x. Okay, so we know that sine is equal to root 3 over 2 in the first and second quadrant. So pi over 3 and 2 pi over 3. So I can replace that inverse sine of root 3 over 2 with pi over 3, and as well as with 2 pi over 3. I'm going to just cross multiply, solve for x in both instances. First instance is x equals 4 pi over 3. That's fine. That's within my domain. But the second one, 8 pi over 3, is more than 2 pi, so I'm going to remove it. It's outside my interval. All right, so from Excel pre-calc last year, one of the final units that we covered was logs and exponentials. So hopefully this is still fresh on your mind. Let's look at, let's work through these problems here. Let's go through the odds so that I have some problems for you guys to also want to kind of make sure I'm able to kind of cover all the topics, and then you guys can finish the remaining for your homework. So let's look at 47. Right, so a couple of properties that's useful. Remember that e to the 0 is equal to 1, right? Anything raised to the 0 power is 1. And also natural log of 1 is equal to 0. We talked about how exponentials and logs are inverses of each other. So if there's an order pair of 0, 1 for exponential, there's going to be an order pair of 1, 0 for natural logs. Yeah.
Natural log is the same thing as log base 10.
Log base e.
Log base
E. Yeah. Natural log is log base e. Okay, so 47, if I want to solve for x, I'm going to first try to get this e to the x by itself first, and then we can worry about that, getting that x by itself at the end. So I'm going to subtract 5 from both sides. Divide both sides by 3. And one of the properties that we learned with logs is that, or exponentials, is that if anytime I want to solve for x that's sitting in the exponent location, I can take the natural log of both sides. And the nice thing about taking the natural log of both sides is now the exponent is free to move. So once we are inside a log or natural log expression, the exponent is free to move without changing the overall value. So I'll take the natural log of both sides. So the special property with natural log is that the exponent is free to move, that x can come down in front. And natural log of 1 we know is 0, so I'll replace natural log of 1 with 0. And another special property is natural log of e is equal to 1. Okay, this is basically saying log base e of e. These will just cancel each other out. Natural log of e is equal to 1, so this goes away, so x is simply equal to 0. Yeah.
Can you just like look at the e to the x equals 1 and just know that x equals 0?
Yep, that's true. You can also go from here and go directly to solve for x that way. But right, but if it was like e to the x equals 2, then you do want to go through these steps to help you solve for x. Yeah, but in this case, yeah, we could jump directly to this. But I want to kind of show you the full steps in case it was equaling a different value. Okay, 49. Natural log of x is equal to 0. I want to solve for x, but it's stuck in this natural log form. So we talked about how natural log is log base e, and it helps to, maybe sometimes it's helpful to rewrite it in a different form so you can clearly see what that base is. And we can convert from log form to exponential form if we understand where the base is. So in log form, your exponent is by itself, but then if we want to get it back into exponential form, understand that's the base, that's the exponent, and that's the value. So e to the 0 is equal to x. This is the same thing, but it makes it easier to work in this form because this is kind of stuck in a form that is difficult to interpret. Okay, so if we know e to the 0 is equal to x, that makes it easier to solve because we know what e to the 0 is. Anything raised to the 0 power is 1, so x is equal to 1. Okay, 51. Natural log of 3x equals 0. Again, if I'm having a hard time interpreting natural log, I can always rewrite it as log base e. So I can see what that base is coming from. And now, if I can rewrite this in exponential form, it's easier for us to interpret. So start with base e. E raised to the 0 is equal to 3x. And you know what e to the 0 is? E to the 0 is equal to 1. And then now we have the easy equation to solve. Divide both sides by 3. X is 1/3. Yeah, a couple of nice properties up at the top to review here. If I can get the bases to match, then I can just drop the bases and set the exponents equal to each other. These are expansion properties for logs. If I have natural log of AB, I can expand into natural log of A plus natural log of B, sometimes splitting up into different smaller parts. It's easier to work with. We know natural log of x, same thing as log base e of x. Sometimes it's easier to rewrite it in a form where you can visually see what that base is coming from. Multiplying base is the same thing as adding the exponents. Dividing base is the same thing as subtracting the exponents. Quotient property, if I have natural log of a divided by b, I can expand it natural log of a minus natural log of b. Special values of natural log of 1 is 0, natural log of e is 1, natural log of 0 does not exist. So there's a vertical asymptote at that point. And then there's this power property. This is really the really nice feature about logs, is that once you're in a log expression, that exponent can just be free to bring down, right? Normally we can't just bring an exponent down in front and have the same value, but for natural logs we can. So sometimes exponents being brought down allows us to move forward in our problem a lot faster. Okay, so let's continue with the odds here. 53, e to the x plus the x e to the x equals 0. I want to solve for x, but maybe it's easier if we think in terms of factors, right? What are some common factors that I can take? What's the common factor shared between these two terms?
E to the x.
E to the x. So if I take out an e to the x, I'm still left with a 1 from this term plus x. So now that I have in factored form, I can set both parts equal to 0 and look for the solutions independently. So anytime that I want to bring an exponent down, if I can have this as part of a natural log expression, then that exponent can come down. So I'll take the natural log of both sides. Now there's already an issue. This left side is fine. We can bring the exponent down, but what's natural log of 0?
Oh, it does not exist.
Does not exist. So we already know that this is not going to be a solution. So we can just cross this out, right? There's no solution there. Okay, let's move on to the other portion. 1 plus x equals 0. X equals -1. Yeah.
So the e to the x equals 0, like not like the last one, like it wouldn't equal.
We know e to the 0 is equal to 1,
Oh.
but e to the x is equal to 0. So here's the exponential graph. The exponential graph looks like this, right? Right. Is this graph ever equal to 0? No, right? But natural log, but e to the 0 is equal to 1, right? There's a y value of 1 there, right? Okay, let's continue through here. Let's go down this column, number 55. We'll do A, C, E, and G. Okay, solve the following. Log base 81 of root 3 is equal to x. This looks complicated because this is in that log form. If I can get it into exponential form, then I'm able to kind of see things a little bit more clearly. So what's my base? 81. So 81 raised to the x equals root 3. So this still looks like it's a little messy, but here's the key thing is if I can get the two sides to share the same base, then I can just drop the base and just focus my attention on the exponent. So 81 and 3, let's see if we can drop them down to share with the same base, right? So maybe we can target 3 as the base. So what's the relationship here? 81 is the same thing as 3 to what power? 3 to the 4th. So I can say 3 to the 4th. And then I want to keep that x because I'm making a substitution with the 81 and 3 to the 4th, right? Making those substitutions. And then root 3 is same thing as 3 to what power? To the positive 1/2. Yeah. Root 3 is same thing as 3 to the 1/2. So now things become a lot cleaner because now the bases are the same. I can drop them and then just look at my exponent to solve for x. Okay, cross multiply. 8x equals 1. So x equals 1/8. Okay, part C, 9 equals 4 plus log base 2 of x plus 3. We probably do want to convert it into exponential form, but right now there's too many pieces, right? So if I can kind of tighten this up and combine some like terms and get it so that I can just have log of base of the value equals the exponent, then I can convert it. But right now it's a little bit too soon to do that, but I can see that 9 and 4 can combine together. Let me just subtract that 4 from both sides. So I get 5 is equal to log base 2 of x plus 3. I'm going to just rewrite it with a log on the left side here. Log base 2 of x plus 3 is equal to 5. So now log form is a little harder to interpret. So let's try exponential form. What's the exponential form of this log expression? Yeah, 2 to the 5th equals x plus 3. And now this becomes a lot clearer to work with, right? Okay, I can solve for x now. I can move some things around. So 2 to the 5th is 32. Subtract 3 from both sides. Okay, part E, log base b of 8 is equal to log base b of x plus log base b of x minus 2. Still, there are a lot of terms going on. If I can get it down to a one-to-one relationship, it'll be easier for me to interpret what's going on. So here I have log base b plus log base b. So we're going to take advantage of this property here. I'm going to merge together. Log properties, doesn't matter what base, could be base E, base B, base 3, the same property still applies. So if I have the sum of two logs, I can merge it to the product of those terms. So I'm going to do that here. If I have basically have log of A plus log of B, I'm going to merge it into log of A times B. So now we see a one-to-one relationship, right? One-to-one relationship, which means that I can drop the pieces that are the same and just focus on the value. I can drop the log base b from both sides and see where that takes me. Okay, any questions so far? Now, can I do this? Can I say, oh, this is factored form here. Can I say x equals 8 and x minus 2 equals 8? Okay, we can't do that. The only time we can do this is if this number is what? The only time I can do factored form and set equal to the other side is when this is 0. Yeah, that's the only time it works. I know it's tempting to say, oh, that's x equals 8, x minus 2 equals 8, but it's not going to work that way. Okay, we're going to have to bring everything over, go through factoring, get equal to 0 first, and then we can do trinomial factor. I know this is tempting. Now, this is 0, then that's perfectly fine, but that 8, we got to do some more work here. Okay, so I'm going to write this as 8 equals x squared minus 2x. I'll bring that 8 over. And I know it looks more difficult because I know it's easier to just go through this process, but it's not going to give you the right answer. We're going to have to go through factoring here. So trinomial factoring. We got to get the 0 to show up before we can set anything, before we can find any factors and any solutions. Okay, so two numbers that multiplies to be -8 and adds up to be -2. -4 and +2. Solve for x. Now we can do this. Okay, so this is fair game. We can do this and set equal to 0, but we can't do this and set equal to 8. Now, there's one more thing that we have talked about in our log unit in the past, is that we can't have a value inside a log that is a negative value. So the 4 is okay. The 4 is not going to cause any of the expression to turn negative, but the -2, if it even causes one expression to be negative, that's gone. We can't have it. So there's only one solution here, x equals 4. We can't have a log of a negative value because that doesn't exist. Okay, part G, e to the 3x equals 6. So depending on the problem, sometimes we want to convert to exponential form because it's easier to work in that form. In this case, we want to get it into natural log form because that exponent is tough to deal with. But if I have natural log form, that exponent can move. So here, I'm going to convert to natural log form. In other words, I'll take the natural log of both sides. The special exponent property that we have is that exponent can be free to move. So I'll move that exponent down in front. It's a lot cleaner now, a lot easier to work with variables if it's at the base level and not at the exponent level. Okay? What do you know about natural log of e?
Zero.
Not
Can't
zero.
tell.
Good, it's 1, right? It's equal to 1. So I can just make it go away. So 1's not going to influence anything. So now 3x equals natural log of 6. Natural log of 6 is some decimal value. So we can just leave it in that form. We can't say this is natural log of 6 divided by 3 is 2. That 6 is inside natural log. It's not free to combine with that 3. So this is the exact value, but it's some decimal value that we don't have to worry about unless we had the calculator.
Can you do H?
Yeah, we can do H. So H is 7 raised to the x minus 4 is equal to 100. I want to solve for x, but x is stuck in the exponent. Let's go ahead and take the natural log of both sides. That exponent is now free to move. We're now inside a natural log expression. That x minus 4 comes down. Now, careful, you probably want to leave that x minus 4 in a set of parentheses so that we don't lose track of the fact that the x minus 4 is together multiplied with that natural log of 7. Okay, I want to solve for x, so I'm just going to go ahead and move things away to the other side. So I have natural log of 7. Just go ahead and divide both sides by natural log of 7. Now your answer doesn't have to be clean. You just have to find a way to get that x by itself. That's really all we care about. So that's going to be some decimal value, right? But I just want to solve for x, so I'll just add 4 to both sides. This is sufficient without a calculator.
It's like 6.6.
Yeah, if you were to enter in the calculator, but right now, I think it's more important that we just understand how to solve these equations.
We always put it in natural, so they have a log.
That's my preference. You can do logs of other bases, but natural log is the one that we use the most. So it's just that's our default. Just use natural log.
So like, what I struggle with, like for this and Trig identities as well, like for exponential log properties, is like trying to memorize like the different properties. Like, what do you think should like can help with that? Like memorize.
Yeah, as far as trig identities, I think you know, there's a lot of them, but really the most important one is this one here. That Pythagorean identity here. If you know this one, then this one will help you with all the other ones as well. Yeah, the double angle, half angle identities, that's not going to show up on the AP exam. But this is probably the one that we most need to know. But you know, if we need to use this, I'll review this with you again once we start trade unit. But we're not going to go as deep as what we did in pre-calc. So we only need just a few things, and I've covered the most important things already for trig. Okay, there's quite a bit from P.4. So I want to see if I can just start hitting various problems, various types of problems, at least one of each type. And the hope is that starting tonight, you can start to fill out some of this homework problem, so you're not having to do all of it Sunday night, so you can just kind of chip away at it. Okay, so let's look on page 13. Okay, so these are some miscellaneous topics. So it says here for the piecewise function. So that means we have some function that is existing to the left of 5, and we have another function that's existing to the right of 5, and we just want to know what are the values. So basically, we just have to decide which one do we use based off of the restrictions. So P of -3. -3 is what? Greater than or less than 5? Less than 5, so we're going to use the what? Yeah, the first one, right? So you use the first expression. So we just insert -3 in for x. Right. So really just as easy as that. You decide based off the restrictions, which value to plug the x into, and then you just find that value. Okay, so go through and try B through D.
If you were to graph that function, how would we do that? It would be like absolute value.
So if you were to graph this function, you probably have to use order pairs. I don't worry too much about graphing it, but typically maybe something like this, where you got the square root of x plus 4, that's to the right of 5 like this, and then x minus 5 squared to the left of 5, so maybe something, yeah, something like this. You got half a parabola showing, and then you have a radical showing. But
Would it be like right to the left of 5? So
oh, I'm sorry. The other way around. My bad. Root x plus 4 is going to be on the other side. And then root x plus 4 to the left of 5. Maybe something like that. Okay. Okay, let's check our answers here. You guys get 1, 2, 3, and 25. Okay. Okay, so a little bit more into trig here. Simplify the following given all the angles are between 0 and pi. So it's saying find sine of 2 arc cosine of root 2 over 2. So let's break this down piece by piece here. So this notation here, arc cosine of root 2 over 2, is basically a notation saying this represents theta. So in other words, if I just focus my attention on that, theta is equal to arc cosine of root 2 over 2. So in other words, this is saying, where is cosine equal to root 2 over 2? Okay. So in other words, where is cosine equal to root 2 over 2? So what's theta equal to? Pi over 4. So I'm going to replace that pi over 4 into this portion there. All right, so I found the replacement for that arc cosine of root 2 over 2, which is pi over 4. So now let's see what that gives us. So I have sine of 2 times pi over 4. Right. Now it's a lot cleaner to interpret, right? What's 2 times pi over 4? Pi over 2. And what's sine of pi over 2? 1. I'll leave B for you guys to do on your own. Again, the key are all on my website. So, if you're stuck on a problem, hopefully I have enough detailed work to help you, as well as the examples that we did together. So let's look at number 3 here. Number 3 says, rewrite each of the following as an algebraic expression with no trig function involved. Hint, draw triangles and use Pythagorean theorem. Okay, so let's focus our attention on just this portion here. Arc cosine of 2x, that's another way of saying is that is my theta. So theta is equal to arc cosine of 2x. In other words, where is cosine of theta equal to 2x? Now I'm going to rewrite this as cosine equals 2x over 1. So we can clearly see the trig ratio involved here. So cosine, SOHCAHTOA, cosine is what? Which side? Yep, adjacent over hypotenuse. Okay, so we're going to draw a triangle in the first quadrant. And we're going to label the size with the variables involved. Okay, so where's the 2x going to go?
It's gonna go on the bottom below it.
Bottom, good, adjacent, right? Okay, where's the 1 going to go?
Hypotenuse.
Hypotenuse, okay? So we're going to find that third missing side. I know that a squared plus b squared equals c squared, so I can say 2x squared plus b squared equals 1 squared. Solve for b. My b is that missing side. I'm going to need that missing side to help me figure out the rest of this. So b squared is equal to 1 minus 4x squared. Take the square roots. So it's a little messy, but root 1 minus 4 squared. There's nothing that we can do to, we can't take the square root of 4 and the x squared because of that minus. So this has to stay the way it is. So now that we have everything in front of us, now we just have to look at the triangle and say, okay, what is sine of theta? What is sine of this triangle? SOHCAHTOA, so sine is what? Over 1, right? Opposite over hypotenuse, opposite over hypotenuse. So the inside information is to help us fill in this triangle. And once we have that triangle involved or filled out, then we just do the sine or the trig of that theta. Now I can drop the 1 because that 1 is in the denominator, so that's fine. Or you can just leave the 1 below. Okay, let me just start 4a, and then we can stop. So solve the following using identities when necessary, given that 0 is between x is between 0 and 2 pi. So I want to solve for x, but I would like to get everything as one trig function. So I have 2 cosines, so maybe it's easiest to just replace the sign in terms of cosine. Now, I just talked about that trig identity. That's really helpful. Sine squared plus cosine squared is equal to 1. So if I know that identity, I can rearrange it, solve for sine squared, and then replace sine squared instead of cosine squared. So I know that sine squared of x is equal to 1 minus cosine squared of x. So that is the substitution that I'm going to make. I'm going to replace this in for that sine squared x. And the advantage there is if I can get everything in terms of cosine, then it's a lot easier to merge things together rather than working with 2 different trig functions. So now that everything's in terms of cosine, let me just bring everything over to one side and see if I can combine like terms. So add cosine squared to both sides. The nice thing is that the 1s cancel out. So I don't have to do trinomial factoring. I just have to take out the GCF, right? So what's the GCF here? Cosine x. Now, if you factor cosine x out, that doesn't become a 0. There's still a 1 there, right? You still have a 1 left over. So now that 0 is fine. We can set both equal to 0 and solve for x and use unit circle values to solve for x. Okay, so we'll pick up tomorrow, but I think it's good if you guys can, up to this point, try to work out the problems So as to minimize the amount you got to do over the weekend, but we'll try to do as much as we can tomorrow for the rest of packet of P4.
Thank you.
All right, come get your phones.
Thank you.
Yeah, thanks.
Out of all these stuff in the packet, what do you think is the most important thing for like calculus? Like, so like.
It depends on the unit, but I try to go through a little of each. But I think right now you don't worry about, well, you gotta memorize all these things, but I think as long as you understand how to do those problems, that's good enough.
Okay, yeah. Yeah, like what I usually do is like, if I don't understand something, I look at the answer key once, see how you started it, and then I do it on my own.
Good, good. Yeah,
I don't know if that's
I
helpful.
think that's great. I think that's great. Yeah.
I just don't want to like cheat or anything.
Yeah.
So,
As long as you are using the key in the right way, I do want you to use it.
okay.
Can I go to the council? Yeah, go ahead. Thank you.
We have a competition tomorrow morning.
Not